So what I'm seeing is a lot of people memorizing the conversion factors, but then having no context on how to manipulate or use them. And this is a common pattern. So we had the previous slide said that, well, 22.4 liters equals, yeah, I know. 22.4 liters equals 1 mole. And since I want to solve for liters, well, then I would need to know the moles that go into it. So this would be my question mark here. Okay? Am I told how many moles? Ultimately, we're going the other direction. Nope, we're going that way. Does it tell you a mole value? Okay, and this shouldn't be like, oh, well, I don't know. Does it say anywhere in the question moles? No. So you aren't told it. That is a perfectly fine conversion to try and run if you have it. You don't have it. Okay? So what can you do? We could go through and say, maybe I should find out what the moles are. Okay? Which would mean another conversion. Okay? That other conversion. So let's go ahead and say moles, and it needs to be related to something. Well, what could it possibly be related to?
Grams.
Okay? Why grams?
Molar mass.
Okay? I heard molar mass. Well, I can go moles to molecules, Avogadro's number. That doesn't make my answer any more valid than molar mass. Okay? In fact, my answer is invalid. Going to molecules is completely meaningless. Why is it completely meaningless? It didn't ask for moles either. Right. We're recognizing, because you memorized a conversion factor, that liters and moles were related. Okay? So I needed to know moles so that I could find the liters. But I don't know the moles, so that's why we brought in the moles. What unit should I pick for molecules?
Grams.
Okay. Why grams?
Because there's grams in the question.
I'm given grams in the question. So if I could figure out what the conversion factor was between moles and grams, now I could do something. Where do I find the conversion factor between moles and grams? That's the periodic table. That is 2.02 grams is equal to 1 mole. How many grams did I start with?
2.
Okay, I started with 2 grams. How do I go from 2.02 to 2.0? We can't subtract. We have to go by scalar multiples or divisions. Okay, we could look at this as really ballpark just times 1, okay, which as far as I'm concerned about is fine at this point, which means what number is down here? Well, times 1. So I get 1 mole is 2.0 grams. Do I know how many moles I have now?
Yes.
Yes, which means I said I had to find it. What do I need to do? Plug it in. I have now found it. I know that is 1. How do I go from 1 to 1? Multiply by 1. So what do I have to do to the 22.4? Multiply by 1, and my answer becomes 22.4 liters. This method works. This is messy. It's all over the place. Okay? If you've got conversion factors memorized and that's how you want to do it, that is fine. You can go through and do that. The problem with it is that logic is still, well, I know a conversion factor. Does this one work? No. Does this one work? No. Does this one work? No. Okay? You're running through every possibility. Instead, that is why we have the process that we've been talking about. What do I want for an answer? Liters of hydrogen gas. What am I given to start with? 2.0 grams of hydrogen gas. Is hydrogen gas the same thing as liters of hydrogen gas? No. One's grams, a mass, one's liters, a volume. So what has to happen? I have to do a conversion. Ideally, what would I convert? Grams to liters. Ideally, both hydrogen gas. Does that conversion factor exist? No. Okay, at least not readily available, which means I'm going to have to convert to something else. Okay, so what do I want to convert the grams to? Why moles? Okay, I know I have a conversion factor for it, which is a good answer. I also have a conversion factor for AMUs. Why should I do moles instead of AMUs? Okay. One option. I remembered somewhere in the back of my head that there's another conversion factor. Come on, pen. That I know 20, and I keep doing that, 22.4 liters equals 1 mole. I have that. I know, hey, liters, that's useful. Okay? Moles, that could be useful too. I could just say, well, I'm stalled here, and I don't know. That's where pulling that information would come in handy, because what you could go through and say is, where should the liters show up from this conversion factor? On the top. Why should I place it in the numerator? That's where it shows up in the answer. Liters up here. What should show up in the denominator? Moles. Why do I place it in the denominator? I'm actually going to disagree with so it cancels. Because ultimately we said I don't know what conversion factor I can convert grams to. I know from the equality those liters must equal moles. So there it is. I can now go through and plug in my value. 22.4 liters, notice I did it right that time, is 1 mole. Well, now what should I convert grams to? Why do I want moles? So now it cancels. I can see the reason for why I'm doing the conversion. Okay? That reason is what drives all of your conversion factors. If you don't have a reason for putting your conversion factor in, you could be putting it in upside down. Right? That's kind of a big deal. What is the conversion factor between grams and moles? Where is that found? Periodic table, because I'm horrible at rounding. We'll just write it as that, periodic table. Where do I find the conversion factor between liters and moles? You memorized it. Okay? This is going to get really nasty now, because I spent a good 10, 20 minutes railing, or probably 10, 15 minutes railing about that conversion factor. Okay? Is that conversion factor true for this substance? Why not? Okay, number one, it must be a gas. Right? That substance, silver nitrate, how do I know that's not a gas? It says aqueous. Okay? So I can't use that conversion factor if my substance was silver nitrate. How do I know I'm allowed to use that conversion factor for this question? Because it says, yeah, hydrogen gas. Fantastic, it's there. Right? But if we flip back, it's not just for gases. Okay? There's another condition that's very, very important. Otherwise, that equation is invalid. What is that other condition? It must be at STP. Where in this question does it say at STP? It doesn't say. What does that mean happens?
You made an assumption.
Okay. You made an assumption when solving this question that it was at STP. Okay. I really hate to admit this, okay, but under most circumstances, when it comes to test bank questions in classes, they're making the blatant assumption that it's at STP, though not stating it. Okay? That is an incredibly important statement to make. Since it is not made, and we know this is not generated by just the random test bank generator, and that your instructor sees beyond these kind of silly assumptions, would we be getting the correct answer? No. Damn it. What would the correct answer be?
Unable to find.
What's that?
Would it be unable to?
Unable to find. There's not enough information in the given question to allow me to make the assumption for that STP conversion, which means I'm dead in the water. There's no way for me to solve this unless I'm given more information. Okay? That is a very important distinction to make. This comes back to using language appropriately. If you don't have the language to support it, you make the question impossible to solve. Right? So we have to have that extra context. Make sense? So how do I fix it?
How many liters in the air to hold 2.0 grams of hydrogen gas at STP?
Perfectly valid change. How else could I change it? Right, how else could I change it? All of those things say the same thing. Standard temperature is 1 atmosphere and 0 degrees Celsius, okay, which happens to be 273 Kelvin. Why show the Kelvin unit? That's our science unit, and that unit will become incredibly important when we actually look at gases to understand why this conversion factor even exists. Okay? So let's double back through this conversion factor because I really want to drive home the point of how insanely dumb this conversion factor is and how limited it is in use. Okay? Number 1, when is it true? Fair enough. Try a different one. With gases, when was the last time you did a gas phase reaction? Never. Okay. But you haven't done any other kind of chemical reactions, right? Oh, you have. Okay. So this equation, this conversion factor, is useful when we work with gases that we don't work with. Okay. What does STP stand for? Standard temperature and pressure. Which one of those two do you want to yell at or have me yell about first?
Standard pressure.
Wow, I forgot. There were 3 words in there and I forgot about the standard part of it. Okay? Our pressure. What is our standard pressure? 1 atmosphere. When is it 1 atmosphere?
Standard.
At sea level. Okay? Are we at sea level? We'd have to check our altitude. For anybody that knows, we are not at sea level, which means standard pressure isn't true. So we do any experiment here, STP is invalid, okay? Because we're not at standard pressure. What about standard temperature? It's just 0 degrees Celsius, which happens to be the freezing point of water. So this conversion factor is valid when you're working with a gas, which you don't do. Okay? When you're at standard pressure, which you aren't at, okay? Arguably you could get to standard pressure even in the middle of the country, like that's possible. Okay? And standard temperature, which is 0 degrees Celsius, which in Phoenix happens maybe once every 2 years. Right? Okay? So that conversion factor, as far as we're concerned in this room, is invalid. Okay? The last one we could throw into it is the word standard, and as we talked about last week, standard isn't standard. Depending on the field that you go into, they pick a different standard. Why? Well, it's standard for my field. That's not a standard. Okay? So, it is a nasty conversion factor to make you use. Are we making you use it? Absolutely. Okay? And I apologize profusely for that, but there's nothing I can do about it. Okay, that is what the field of chemists in this state have decided should be addressed. Okay? So, we have our conversion factor. We can use it just like any other. So now what we'll go through and do is manipulate that for another question. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid at STP? Set it up. You've been using stakeholder analysis. If you don't know how to solve it, start putting together. This is what I want. What are the pieces of information that I might need to go through to be able to set up this conversion? Okay. You probably haven't even filled out your entire stakeholder analysis. You've got at least a couple people have the bottom rungs. You could even use those bottom rungs to try and figure it out. Set up the work. Equals is always a good place to start. Equals what?
Liters of hydrogen.
Liters of hydrogen. What is our symbol for hydrogen? H2. It'll only become H if we say atoms of hydrogen or hydrogen atoms. Okay? So now the question, what do we start with?
What's given to you?
Okay? So a suggestion was made that we should just start with what was given to you. What was given to you, in your opinion, because that was your suggestion to start with?
0.165 grams of aluminum.
0.165 grams of aluminum. And give me a sec. I would argue that's a good place to start. And then, let's see where your and then goes.
And then I would do some formula there to balance it.
Okay, so I would argue balancing the formula I wouldn't quite use yet. I want the intent. Why are you balancing the formula?
If it gave you a formula, you probably got to use it for something. If you want to use it, then it's got to balance.
Does everybody hear that as an intent? The intent is, he wrote it down, he probably wants me to use it. Okay? That's fairly legitimate. Okay, I'll accept that. There's a better intent. So, molar mass isn't going to matter because all I need is the correct formula, so I don't accept that as an intent. Ethan, you had an idea?
You're going to need the conversion.
Okay, again, we got the idea. I know eventually I'm going to need this information, but that legitimate, solid intent, I need that coefficients to convert what?
You're converting to the hydrogen gas.
Hydrogen gas from aluminum. What is the unit change as I look across the question? The measurement changed and the substance. How do you convert substances?
Balance.
Through a balanced chemical equation. There's the intent, not, you provided it, probably need to use it. Okay? That's possible, right? But we can write questions where we provide a crap ton of stuff that you're not supposed to use. Okay? So you got to be a little bit careful on that. The intent here is because the substance changed. Aluminum to hydrogen, that's a different substance, which means I'm going to need a substance converter. The only place the substance converter is found is the chemical equation. And in particular, what type of chemical equation? The balanced chemical equation, which in this case, it's not balanced. So I would have to go through and balance it.
2623.
Thank you. I was just going to guess and hope I was right. 2623. This is a harder one to balance. Based on experience that I've gone through and seen with people balancing, is that you will probably cycle through 4 times. You check the first one, it's balanced. You check the next one, it's not balanced, so you change numbers. And then you continue to cycle through like we did in Unit 2. Okay? So you have to use that skill to balance this. Now that it's balanced, we can show a conversion between aluminum and hydrogen. And that is fantastic. I now have a substance converter. I can get rid of the aluminum. Why would I place it in the denominator? I want that unit to cancel. I don't want aluminum to show up. What do I want to show up? What substance do I want to have show up? Hydrogen. Okay? That is now my substance. Okay? All units must be complete, a measurement and a substance. Right now, all I have is substance. I need the measurement unit. What measurement unit am I allowed to use from a chemical equation? Moles. Why would I pick moles and not molecules?
Because molecules doesn't make sense.
Molecules doesn't make sense. Why? I can go moles to grams, but I could do AMUs to molecules. So there's an interesting idea. We're in units of grams. AMUs to molecules would work, but I'm not given AMUs, I'm given grams. So since I'm given grams, I know there's a gram to mole relationship, so that could work. What's another idea that we could potentially use for this? How many of you will ever work with molecules?
No.
Why not?
Not.
Not quite too many, but getting at the right idea. What's the issue with working with molecules?
Too small.
They're too small. Okay? So when we use the word molecules, like if I said there were multiple chairs in this room, we'd probably be okay. But if there were 20,000 chairs and there are now chairs in the world, you might be like, well, yeah, but the scale there doesn't really make any sense. There's a hell of a lot more than just chairs in the world. There's probably millions of chairs, not billions of chairs. It might help to reference that. Okay, like someone says, oh, can you go buy some eggs for me at the store? And you come back with a dozen eggs, and they're like, no, I asked for eggs. You're like, yeah, there's a dozen eggs. No, I wanted 52. You didn't do what I asked. Okay? There's a scale difference. So molecules doesn't make sense as a measurement because we probably won't work at that scale. Since we're running an experiment, it makes sense to scale that up. So we want to use moles instead of molecules. What is the conversion, numerical conversion factor that comes into this?
3 to 2.
3 moles of hydrogen and 2 moles of aluminum from the balanced chemical equation, those coefficients. The problem with using this conversion factor first, what happened with my units? Nothing canceled. Okay? I did at least bring in moles of hydrogen, but that didn't help me out. So there were some people that had suggested that I wanted to convert to moles first. Moles of what?
Aluminum.
Aluminum. Because what you were trying to do was get rid of grams of aluminum. Okay? And my argument would again be, well, why are you doing that? Are you converting to moles just for the hell of it? Okay? I would argue you had a solid foundation. Grams became liters. The substance unit or the measurement unit changed. So trying to change the measurement is probably a good idea. Can I go grams to liters?
No.
No. Could I go gram? There's a bunch of other ones I could go through and use, right? Or at least one other one. Okay. This is going to be the best one. Where can I find that conversion factor? In the periodic table, which tells me 6.98 grams is 1 mole. This is now a neat conversion factor because what happens? Lots of canceling happens. Okay? Do I have my answer? What do I need to do?
22.41.
I'm going to freak out. You should know this by now. Don't give me numbers.
Liters of hydrogen.
I want liters of hydrogen in the numerator because
That's the answer.
that's where it shows up in my answer. What do I want in the denominator?
Moles of hydrogen.
Moles of hydrogen. Okay? Where does that conversion factor come from? 22.4 liters is 1 mole. You're told to memorize that. You can now punch this into a calculator.
We should punch it into the calculator, because we didn't think that the same stuff, but we got a different answer.
How different?
Pretty different.
Pretty. It's like 0.8, mine's like 0.2.
That's not that different. That's probably using 26.98 versus 27, would be my guess.
So I had a question about why it was liters of H2, since it said liters of hydrogen. Is it because liters is a volume measurement, and so that would automatically be H2?
When can you write?
Hydrogen's diatomic.
Well, I know that, but it just said hydrogen. It
When
didn't say
can you
hydrogen.
write just hydrogen as a single hydrogen? Yeah.
Only if it's the atoms.
He did like
Only
1.5.
if it says specifically atom. If it does not specifically say atom, you can't do it. I see 22.41.
Oh, that might be it. Yeah.
I'm gonna bet you that's why
That's probably
it
it.
shifted off. Your work, both of your work looks fine, so it's just gonna be a calculator issue. Kinda, sorta? Sorta, kinda. We're gonna take a break. And by a break, we're not gonna look at conversions for a little bit. We're still gonna talk. Okay? Atmospheric pressure. So one of the things that we can do with gases is talk about how they exert on their external environment. We can get the gas pressure. This is the force of the gas particles literally pushing on the sides of the container. Okay? We have gas around us, so there is a pressure around us. Okay? So the way this was initially monitored is someone took a tube, okay, with a liquid in it and inverted it inside a larger cylinder with liquid. What would you expect to happen to the liquid in the tube? Okay, let's say this was a straw. What happens to the liquid in it?
Should stay.
It stays?
Well, if you have your finger over the straw.
When I suck up liquid out of a straw, right, and then I stop sucking on it and just take my mouth off, what happens to the liquid?
It goes down to the.
It goes down. So what would you expect to happen in the liquid? It should probably go down. Okay? Like most things, when I hold something up and let go, it falls. Like that makes sense. Okay? If I take liquid and I do the same thing, it falls. And so somebody got wild hair in to try this out. And so they flipped it upside down and they noticed it fell. But not all the way. In fact, it stopped fairly high up the cylinder. Well, why is it doing that? What is causing the liquid to fall? Gravity. Okay? It's particles, or it's gravity, the force of gravity pulling that liquid down. Okay? What would cause it to stay in the tube? Something has to be pushing down on the liquid outside so that the liquid inside the tube stays up. What is that something pushing down? That is atmospheric pressure. Okay, so the thing that's interesting about this is that if we take the cylinder and we move it from different altitudes, we notice that the liquid level changes. Why would it change? The atmospheric pressure changes. We might say, well, that's just weird. I'm going to stop moving it up and down, and I'm just going to leave it in one location. Okay? And we're just going to watch it because we got time and we like watching paint dry. Okay? So we watch it for long enough, and what happens to the height of that liquid? We would assume nothing, right? Because we aren't changing the altitude. What happened to it? Moved up and down. And not just down, it also moved up. Why would it move up and down? What's changing? Atmospheric pressure is still changing. Okay? So one of the things that we happened to notice was that when the pressure or when the mercury fell down, the weather changed. When the mercury went back up, the weather changed again. So weather changes are tied to atmospheric pressure changes. Okay? Hence the birth of meteorology, where they look to see the effects of pressure and tie those back to weather patterns. Okay? So we could just hide one of these in our room and just be like, well, what's going on? Oh, I can go out and tell all my friends it's about to rain. Watch out. They probably would have just looked up at the sky and just been like, yeah, I can see that. Okay? But maybe if you did it more appropriately, you could predict a little better. Okay? So we could see those pressure differentials. Okay? Because we now have something that we can tie this observable phenomenon to that's actually kind of cool, like a weather pattern change, we need some way to quantify it. So how could I quantify the liquid in that tube?
Little dashes.
I could put little marks. What am I marking on those little markings? Okay. We could try and deal with temperature. That's a possibility. I would argue we don't want to do temperature because what are we monitoring? Pressure. Okay? Millimeters. Millimeters of mercury. Why would you say millimeters of mercury? Okay, the medical field uses millimeters of mercury. What they're talking about is the height of the mercury in that cylinder. Right? Standard atmospheric pressure is 760 millimeters mercury. Okay? What's the issue with millimeters? What kind of a measurement is that? Let's avoid small. It's a measurement of length. And what's interesting about measurements of length? We have feet, we have inches, we have centimeters, we have millimeters. Could all of those be used to measure the height of the mercury tube? Yep, which means what would you need to do with students? You would get to convert them. Yay, conversions. Okay. Before, again, we get into that, we'll cover another little base here because this is kind of nice. Okay. Typically, when you look at these experiments, they're almost always mercury. We rarely use water. Okay, or other substances. What would happen if I used water? The water evaporates from down here. If the water leaves from down here, what happens to the water in the tube? It comes down to replace the water that evaporated. So the water is dropping due to evaporation, not due to an atmospheric pressure change. With mercury, the special thing with mercury is it doesn't evaporate easily. Okay? That property we now name, the ability for a liquid to transition to a gas or evaporate on its own versus not. That concept is known as the vapor pressure. Okay? Water has a relatively high-ish vapor pressure. Okay? Well, pressure is tied to gases. So when we're saying vapor pressure, we're saying when I take a substance, a liquid substance, that it always has some gas. The gas that it makes exerts a pressure. That pressure, vapor pressure. Mercury, on the other hand, does not transition to a gas phase very quickly, which means what would its vapor pressure be? It should be very, very low. It doesn't go to the gas phase easily, which means there's no gas. If there's no gas, there's no pressure. Okay? So different substances work for different purposes. Mercury tends to be really good at this because we don't have a vapor pressure that alters how we measure things. Okay? Same reason why mercury was typically used in thermometers, because it doesn't build up a vapor pressure that would change with temperature, which is the other part with this. If I heat up a liquid, does the vapor pressure go up? Yeah, why? If I hit the boiling point, what happens to vapor pressure? It's all a gas, right? So I would have a massive amount of pressure. So the more heat we put in, the more movement, the more particles we get into the gas phase, which means more pressure. Okay? And we'll worry about the dissolving one later. So units of pressure, right? The standards that came out were millimeters of mercury. That's where we got our 760 millimeters mercury. Tends to be kind of the universally one that's talked about. Okay? But we also have atmospheres. We have inches of mercury. We have centimeters of mercury. In fact, those inches, centimeters ones all seem to kind of make sense because they're all based off the same thing, the height of the mercury in the tube. What is atmospheres based off of? I actually don't know. So when you say altitude, you could be right. Honestly, don't know. Okay. Torrs, PSI, kPa. Okay. Those are all slightly different unit systems for slightly different areas, or what we were trying to measure. Okay. Which of those do you think is the most important for you to memorize? kPa. Why kPa? kPa does show up a lot. Okay, you're shaking your head no. Why are you shaking your head no? Okay. kPa shows up a lot in physics.
I love what you guys are doing here because you're saying it shows up a lot, and that's actually something called corpus linguistics, where you count the number of occurrences of a single piece of language. Linguists eat that stuff up. But anyways, sorry.
Okay. So let's try it another way. Which of these do you want to be the one that's most important? ATM. Why ATM?
It's one.
It's 1. Anybody see in the middle of the slide, roughly, kind of bold letters, red formatting, saying 1 ATM? Guess which one's going to be the most important for us? 1 ATM. There it is.
I already know it's in red, so maybe we won't use it.
That's our standard. That's the one that we're going to focus on. Okay? All the other ones, if you want to convert them, have fun. I'm not going to ask you to convert. Okay? So, the next part, what happens with our pressure? Are there things that affect pressure? Okay, what things affect pressure?
Piers.
Touche. Let's try again. What things affect gas pressure? Beans. Sorry. My turn. Volume. Okay, I heard a relationship between pressure and volume. What happens with those?
As the pressure goes up, the
Less volume, more pressure.
Okay. If we increase the pressure, would we increase the volume? So the example I typically like to use is to help us out with this. We're all in a reasonably sized room, right? 20 by 20 by 15, yeah? Let's switch that to now a 6 by 3 by 3, which is a coffin, okay? So we're going to put you inside a coffin, and we'll close it up so you can't see anything. And then I promise we won't bury you, but we might throw sand on the top of it to make you think that we're burying you. What's going to happen to your pressure? Your pressure is going to increase, right? What did we do to the volume? We decreased it. Pressure and volume are inversely related to each other. The smaller the space, the more pressure. Okay? The larger the space, the less pressure. Okay? Probably because you could just disappear and you wouldn't have to worry about it. Okay? What else could we tie to pressure? We could tie temperature. Okay? And we're hearing directly proportional, which means if I increase the temperature, what happens to the pressure? It also increases. If I increase temperature, what happens to the motion of the particles? They rapidly move around. So they're moving more. The more they move, the more likely they encounter not so much each other, but the wall, because the wall is what's determining our pressure. And you're right, they still are exerting a pressure on each other, but we can't monitor that as easily. Okay? So it's hitting the walls of the container. The more they hit the wall, the more pressure we measure. Okay? Another one? I'll accept that one. That doesn't deal with volume, pressure. What is the relationship between temperature and volume? Okay. Has anybody seen a hot air balloon? Right? The hot air balloon's nice little deflated little things, right? What happens to get the hot air balloon full? What do? You heat it up. You aren't doing anything else, you just add heat. And what happens? It expands. So what happens is I increase temperature to the volume. It increases the volume. They're directly related also. Okay. Last one that we could look at with pressure. How about the number of particles? If I have more particles, what happens to the pressure? Well, if there's more particles, what are they doing? They're going to be hitting the sides of the container more frequently, and we're going to see an increase in the pressure. You'll notice with temperature and volume, we picked nice, easy variables. I don't have one for the number of particles. Okay? Do I have a name for the number of particles that would match something that we've talked about? As a hint. Yeah, there we go. Moles. Moles is our number of particles that we'd be working with in most chemistry situations, because we're looking with a large number of particles. Okay? So what should be the abbreviation? What should be the one-letter code that I want to use? I might use lowercase m. Okay? What's the issue with lowercase m?
Meters.
F equals ma. Mass, not moles. I have another suggestion for meters. M is already used in too many different places. We don't want to use moles. There's a reason we started with something other than moles. The symbol we use is N for the number of particles. The number of particles will get measured in moles. So ultimately what happened is these observables that you guys already are aware of and have used and have seen were also things discovered by long dead scientists. Those long dead scientists got to attach their name to that law. So you'll hear of Boyle's law. Well, Boyle's law, he just studied the relationship between volume and pressure. Right? Temperature of a gas. We can see Charles' law, volume and temperature. You mean just by inflating a hot air balloon, I could attach my name to a law that now people have to memorize? Yes. Okay? This is one of the reasons why I think some of these things are a bit silly. Admittedly, remember when they discovered it. Like 1700s. Okay? So they're long, long dead. As far as the actual names, don't stress about those. Stress more about what are those relationships. As long as you know what those relationships are, you're golden. Sorry. somebody smarter than all of these guys went through and took all of those things and put them all together and said, well, all those relationships were related to each other by a constant. And they defined that constant. They defined that constant as R, the gas constant. So what they saw was that pressure times volume divided by moles at a given temperature always equaled the exact same thing. Okay? We now have the gas constant, 0.0821 atmospheres times liters per mole times Kelvin. That is an important conversion factor which should be on the front of your exam, but I didn't put it there. I will go through and put it there. Because I don't expect you to memorize the 0.081. I do expect you to memorize the equation down at the bottom, but nobody likes fractions, so what could we do? We could rearrange it. There are a variety of ways that we could rearrange it, okay? And I probably shouldn't have advanced the slide because I don't want to look at those ways. We could rearrange it to become PV equals nRT. Why? Because now we can say pivnert, not pervert. Okay. It would kind of work, okay? But pivnert, okay? You are responsible for knowing pivnert. If you have to move into 151, you'll be doing pivnert equations at the yin-yang. Okay, that's why we have to call it pivnert and not pervert, because that gets bad really fast. Okay? So, ultimately what these things allow us to do is we can now solve for any one variable, assuming we're given the rest. So I have 4 independent variables, pressure, volume, moles, and temperature. As long as I'm given any 3, I can solve for the remaining by rearranging the equation using fun little algebras. Kind of, sort of?
And this is actually a version of analysis because you have to understand the roles of each of those things in the larger system to be able to come to conclusions based on those relationships. So that is being able to decode this and understand how the pieces fit together is analysis in and of itself.
All right. So one of the things that we can do, and I'm not going to walk through in as much detail here, is that because R is a constant, is I can take a gas under one set of conditions and I can change those conditions. In the process of changing those conditions, I can now solve for a missing variable. Okay? It's kind of a silly thing to go through and do, but we could go through and do it. The volume of a container is doubled. Assume the temperature and moles are not changed. What happens to the pressure? Okay? So what we can do is set these two expressions equal to each other and start to weed out information. Whoa! What's the weed out information?
Volume is doubled.
Okay, the volume is doubled, which means volume B is twice that of volume A. What happened to the moles?
It says to assume they're not changed.
They are not changed, which means NB is actually NA. What happened to temperature? Same thing. Which then means all of those guys cancel out. And I could now solve for pressure B. Pressure B would be equal to pressure A times VA over 2 times VA. Yeah? What happened to our pressure when we doubled the volume?
Got cut in half.
It is now half as large. So I can use PV equals nRT to solve for these equations, or to solve for those numerical relationships. That can be nice and handy, much more so for future chemistry courses. All right. This one, we're going to do a race. So set it up, solve for this. How many moles of neon gas occupy 2.34 liters at STP? Okay. By the way, while you are solving for this, because it is a race, I will be solving also, but I have a handicap. That handicap is you guys should already be solving it. And you should also not be looking at my work. How many people are following my work? Nobody. That's good. You shouldn't be. If you're following me, you're probably being like, what the hell is he doing? Which is exactly what should be happening. So you shouldn't be following what I'm doing. Anybody solved it yet? Because I'm pretty close. Anybody solve it yet? Okay, I appreciate the racing. As a calculation, I need somebody to enter into the calculator for me because I can't quite do it all on my own. 0.0821 times 273. Actually, that's a lie. We'll just stop right there. We can pause. Did everybody attempt to solve it this way? Good. You should be saying no. What did you do? How do you convert liters to moles? 22.4 liters is 1 mole. When is that true? Standard temperature and pressure. Are we there? Yes. When else does it need to be true? Has to be a gas. Are we a gas? Yes. Cool. So there it is. Orange versus red, purple, and black. Okay. Here's for your little fun and amazement. Take 0.0821 times 273. What do you get?
22.4.
So for those of you at home, you got 22.4 liters is equal to 1 mole. In black, what do I end with? The exact same thing that you started with in orange. All right. 22.4 liters equaling 1 mole is valid for an ideal gas at standard temperature and standard pressure. PV equals nRT is valid when? For an ideal gas. Why bother you to memorize the 22.4 liters is 1 mole when we have PV equals nRT? Good freaking question. I got no clue. Other than 22.4 liters is equal to 1 mole is a conversion factor to make you memorize so that you can prove that you know how to do conversions. Because none of the other things we did helped to show that you knew how to do conversions. Okay? We will pick up there on Thursday. We will undoubtedly be a bit tight on time on Thursday. You should show up ready to go with some conversions.